All right, this is something else that you can do with the online tone generator. If you have two speakers again, so there is a option here to go to binaural beats, and what it's going to do is it's going to play one sound out of one speaker, one sound out of another. So just for reference, 500 hertz sounds like this. Let's make sure this is loud enough so that hopefully this is picked up by my computer. If we then change the frequency of 1 to be very close but slightly off, there's no way for these two waves to be perfectly in phase with each other, and you get something else going on here. So let's play it. And you should be hearing some sort of oscillation in volume up and down. I'm gonna have to end up checking the video to make sure that this actually worked, because I can never tell what the mic is picking up here. If I make the difference a little bit bigger, instead of the difference of 2 hertz, we'll make it a difference of 3 hertz, and that volume oscillation ends up increasing. Let's do that a little bit more dramatically, a difference of 6 hertz, then you should be able to hear an even more rapid oscillation of volume. Maybe the last one I'll do is 10 hertz. And what's happening is it's getting more and more rapid. So this is something we call beat frequency. If any of you are in the orchestra, a lot of times this happens when somebody is slightly out of tune. And what I've done is I've basically played two sounds that are very close in frequency to each other, but slightly off. This is the idea behind beats. So this is a function of superposition as well. When you have two sounds that are very close in frequency, what ends up happening is that they are close in frequency, but they're slightly off. So if you look at the overlap between these two waves here, there's no way for them to be in phase. Sometimes you have crest on crest, but other times you have crest on trough, and they're either going to interfere constructively or destructively. And you as a listener, you can't pick out the individual waves. What you can pick out is the superposition of the two. So you hear this. This is the sum of those two waves, and sometimes it has a large amplitude and other times there's no amplitude. So this oscillates between loud, soft, loud, soft. That's that beat that you're hearing, and this is the idea behind beat frequency. Now what you should have noticed is that the frequency was actually increasing when I had a larger difference between the two frequencies. Now the reason that ends up happening is that your beat frequency is literally determined by the difference between F1 and F2. So when I had the 500 and the 501 playing, the beat frequency would literally be, I think we played 502 first, right? It would be 2 hertz, which means that you hear 2 volume oscillations per second. But when we did a difference of 10 hertz, we get a beat frequency of 10 hertz, so we hear 10 volume oscillations per second. Pretty simple, very easy calculation. The other thing that you're going to see in that PowerPoint was that there was this frequency of oscillation. Think of it as pitch, and you got two sounds playing, right? They're both very, very similar, but what ends up happening is that you get the average of the two pitches here. So if we simply look at F1 and F2 and divide it by 2, the pitch that we would have heard for this one is 501. Now I can't tell the difference, and you probably can't either. The pitch that we would hear here is 505. Alright, so that's an interesting phenomenon, and again it proves that you can get sound waves to cancel each other out at certain points.